So I'll give you a brief introduction into the next project. So the next project that I worked on, and one of the reasons I was invited to come, was to present on some of the testing that we did for the Ohio Department of Transportation. We worked in collaboration with Gresham Smith and Partners, and it was to evaluate the performance of catch basin inserts on Ohio roadways. So, and I can go through some of the introductory part of this, but we all know what a catch basin is, right? So this is getting in post-construction stormwater applications where we have catch basins in urban areas. When you have stormwater that flows off an impervious surface, it's going to pick up a lot of pollutants, right? You're going to get any kind of sediment, you can get oils, greases, trash, debris, you name it. That is all being conveyed into a catch basin. So we focused on type 3.8 catch basins, all the water conveyed in there, and then where does it go when it goes into a catch basin? I'm testing everybody, that's a question. It goes straight to a local water body or a river, right? So what we're trying to do here is there are proprietary practices called catch basin inserts that you can install within the catch basin itself in order to capture some of that sediment, that debris, maybe it'll pick up some of the pollutants, so on and so forth. So the intent of this particular project that we were in charge of at Auburn was to evaluate the performance of catch basin inserts when it came to the amount of sediment they were able to capture. I think that looks good.
Just go to the
next slide. And I installed mine because that one wasn't working.
It wasn't?
I'll use whichever one works.
Right.
So again, we're evaluating the sediment removal efficiency of catch basin inserts. That's you.
Yeah, I'm busy.
All right, you can go back. You're giving away all the slides.
Oh, this is hang on, let's go back to the old one, right?
All right, so everybody understands what catch basin inserts are for, right? So there's three types of catch basin inserts. We have a bag type, we have a basket type. This is perfect. We can move on to the next presentation. So we got bag type, basket types, and then we have cartridge types. So there's a whole variety of these different types of catch basin inserts on the market. And what we ended up doing from a project standpoint, working with GS&P, we narrowed it down to 8 that we thought were viable options for evaluation at the lab and in the field. So with that, we used Google Maps. We looked at an aerial site of what a typical ODOT roadway would look like. We identified the locations of all these catch basins. And then we tried to identify what the drainage area was, the typical drainage area that would go to each of these catch basins. So I got a slide, I'll show it in a second, that has a section of roadway. There's 16 catch basins, and we kind of figured out what the drainage areas were, and they range from 0.1 to about 0.25 to 0.3 acres draining into each basin. So what we were doing, the reason we were looking at this as part of the research objectives was to come up with an effective testing methodology to evaluate these inserts in the way that we wanted to make it as realistic as possible. So we looked at these different inserts and we came to the realization that we were going to replicate a small, medium, and a large drainage basin, which was 0.1, 0.2, and 0.3 acres. And then from there, we wanted to figure out the volume of flow and then the flow rate that were coming from these drainage basins into these catch basins so we can simulate it out at the lab. So as part of the design, we kind of did that, and we're getting there, I assume.
Yeah, we lost the cursor for a while.
So we designed for, again, a typical drainage area. We looked at water quality volume and water quality flow from the Location and Design Manual version 2 that's used in the state of Ohio. So there's 2 formulas for water quality volume, water quality flow. We put in the drainage acreage. There's a couple coefficients and constants that go in there in terms of the intensity of rainfall which was 0.65 inches per hour. That helped us determine the water quality flow. Okay, we're going. All right, so we went through the introduction. We understand that pollutants get into catch basins. We talked about 3 different types of catch basin inserts that are out there that are used to capture trash, soils, chemicals, and other pollutants, and they're prefabricated. They're made to fit within existing catch basins, and the one we were focusing on was a Type 3A catch basin. So these are just the general objectives. So the first one was to develop a testing method at full scale to evaluate the performance of these inserts. So we had to develop a testing regime, what were the influent characteristics, and how were we going to evaluate these products, and we wanted to represent ODOT field conditions. So from there we constructed a test apparatus, which is kind of cool because we can adapt it to any geographic area now depending upon what their needs are, and then we're going to evaluate and compare 8 different proprietary catch basin inserts based upon the amount of sediment they retained and when overflow occurred during the particular test. So this was the aerial photo I was talking about. So we identified 16 different catch basins just in this typical section of ODOT roadway, and you can see the drainage area distribution range between 0.1 and 0.3. Okay, so this is how we're trying to make it like field conditions. So again, using the Ohio Location and Design Manual version 2, we were able to determine the water quality flow rate using the equation on the left. There's a coefficient of runoff, there's a rainfall intensity, and we just had to plug in the drainage area. So that gave us our flow rate for a small, a medium, and large drainage basin. And then we also determined the water quality volume. Again, the precipitation was given to us in the manual, which is kind of the annual average precipitation in Ohio. There's a drainage area that we inputted, and then the coefficient for runoff for an impervious surface was 0.9. So again, you can see in the table in the bottom, we had small to large drainage area from 0.1 to 0.3. We calculated the flow rates, the volumes. If you take the volume divided by the flow rate, we could determine how long we needed to run a test to mimic field conditions, which was 70 minutes. We used 2 different soil types. We used a sandy soil, an OK110, which was specified in ODOT's standard specification 995, and then we also used a sandy loam. I wanted to show you this chart because you can see the particle size distribution of these 2 soils is much different. One is pretty consistent in terms of the size, and then the other one's slightly diverse, which is that sandy loam. So again, the ODOT standard specification 995 calls for this silica sand at a concentration of 450 milligrams per liter. The TARP protocol called for a sandy loam, and it should be introduced at 185 milligrams per liter. So knowing these concentrations, knowing the volume, the flow rate, and the acreage, we were able to determine how much sediment we would need to introduce for a small, medium, and a large flow rate test. And you can see the weights for the silica sand and the sandy loam, and that's what we used in terms of part of our soil introduction protocol. So the way that we tested each insert, we would first do performance-based testing. We had fresh inserts for all the performance tests. We would test one insert at a low flow. We would pull it out. We'd put a new one in. We'd test it at medium flow, and then we'd do a high flow. They were all 3 brand new inserts. We were trying to see whether or not they could retain 80% of the sediment that we introduced, because that's what Ohio EPA's requirement is when it comes to water quality. So we were trying to see which flow rate they qualified for, and then from there we were going to do longevity evaluations, where we were going to put an insert in and we were going to run back-to-back tests over and over on the same insert to see how long it would last, see degradation in performance before maybe maintenance needed to be done on them. So this is what our large-scale testing apparatus looked like. This is just from a schematic standpoint. I have pictures of each one of these components just from taking pictures of the apparatus. You can see there's a water and sediment introduction system on the left. Water flows down our conveyance onto a platform into the catch basin insert, and then we can see where effluent discharge is, which is another one of our sampling points. So this is just a water introduction system. You can see there's a 300-gallon polypropylene tank that we use to equalize flow that we're pulling from an on-site storage pond. We have a 90-degree V-notch weir that was calibrated using a water level indicator so we could vary the flow rate when needed. All of it flows into that influent collection flume and into the conveyance pipe. That gray box there was a NHEC feeder that augured and metered sediment in at a controlled calibrated rate that dropped it into the sediment introduction location that went down our conveyance. We ended up having to put a box around it and put a piece of PVC over it because if wind blew, you'd see sediment kind of being lost in the wind, and we wanted to make sure all the sediment we introduced went into the flow conveyance. So we put a housing and a sediment introduction cover over that area. So all of this flows down this flow conveyance. We put a transition intermittently in that length of 20 feet to cause some turbulence to get things suspended before it discharged out onto the platform. And this is what the discharge platform looked like. We were trying to mimic how water would shed off of a roadway into the type 3 catch basin. So we had the discharge point, and then we had a dispersion flume to kind of put it out as sheet flow. This is what it looks like in the low flow condition, and this is what we called sheet flow introduction. So we learned a lot through the research. For high flow, we would have to move it all the way back here so it could spread out over the platform before going into the grate. This is what it looked like for medium, and then this is what it looked like for low flow. Through a lot of testing, all the water would flow into the catch basin, which was completely sealed, but water would find its way between the catch basin and the inserts, and some would bypass the inserts untreated. So what we eventually decided to do through discussions with Gresham Smith and ODOT is to get rid of the sheet flow because it had its inherent problems, and we went to a direct discharge system where we directly discharged all the sediment-laden water into those inserts so we didn't have any question of whether the water was treated or not. On the downstream end, it would all kind of come into this collection platform, and then we would collect our downstream sample at that location that you see there to compare upstream to downstream to see if we had any reduction in TSS. We developed a non-proprietary version of a catch basin insert. I actually had my graduate student working with my mother. He learned how to sew to develop this just to showcase this, and we wanted to see whether or not the apparatus worked. So he developed this real quick. We stuck it in there, and we ran some tests on it. So you can see from a low flow, a medium flow, and a high flow condition, you can see at the medium and high flow, there'd be way too much water coming in, so the water would flow through the bypass overflow cutouts that we had put in there. And what we wanted to do is to see how this actually worked. So we looked at how much sediment it retained. So we knew what we were introducing. We knew what would end up in the bag. We would dry it. We would take pre and post weight measurements to determine how much sediment was retained. And you can see in just this quick practice that we put together, we retained anywhere from 62, 65 to 50% as it increased in flow. And then we also looked at TSS removal, which was in the 50 to 60 range, by comparing upstream and downstream samples. With some of the CBIs, we had clogging issues, and this is what you're trying to avoid on a roadway, where if it becomes clogged, if it doesn't have an overflow mechanism, it's just gonna flood the roadway and cause a potential hazard to motor vehicles. You can see it eventually kind of went through, sediment was left on the platform, but we identified this as a potential issue with some of these products. To quickly kind of get into some of the results without disclosing what products are which, this is just product comparison. We did a multilinear regression to evaluate one product against the other. We had 3 baskets, 4 bag types, and 1 cartridge. You can see the basket number 1, which we call A, was the best performing, so it was statistically better performing than any of the others. There was 1 bag that was statistically significant lower than all the others. And then all the letters that you see above the other rows just basically shows that they were statistically equivalent, and there was no statistical difference between, we'll say, like bag 2 and basket 2 and bag 1. So you can see there's a variety of performance. There was one that was really good, there was one that was really bad, and the rest of them I would say are in the middle of the road. And this was just looking at sediment retention. Then it also got us thinking about, well, what is affecting the performance? You know, is it the flow rate? Was it the discharge method? Or was it the soil type that we used? So we continued to do a little bit more multilinear regression. We noticed that if we looked at flow rate, which is that second row, there was a statistically significant difference in sediment retention when we went from low to medium to high. So if you have a negative number for your coefficient, that means we lost sediment when we went from low to medium and then from medium to high. You can see our discharge method, the base was our sheet flow versus the direct discharge, and we had an improvement, a statistical improvement in sediment retention when we went to direct discharge, and it actually improved it because more of the water was flowing into those devices. And then when we got down to soil type, you can see that the p-value is greater than 0.05, so it's not statistically significant that there was differences in performance based upon the sandy loam or the sand itself. The last thing I want to show you is our overflow analysis. So what this shows is sediment retention on the y-axis and then the percent of the storm treated before overflow began. So what you can see is this is the low flow rate, and you can see our sediment retention values range between 40 and 80%. When we go from low to medium, you can see overflow starts quicker, less of the storm is being treated, and overall sediment retention values are going down. And then when we go from medium to high, you see that trend continue. When you get to the high flow rate, those systems, they get clogged, overflow, or they become overwhelmed because there's too much flow going in them, and overflow occurs a lot sooner than in the low flow. And then this is what it looks like for the low, the medium, and the high. Longevity tests, again, we put new inserts in. We ran back-to-back tests on them to see once they would get to that point where they really weren't going to perform very well. And you can see for all of the catch basin inserts we tested for the different soil types, every time you test it, the cumulative sediment retention went down over time. And some of them never even reached that 80% mark right off the bat with a new fresh insert being installed. So we saw this degradation. Once it got below a certain threshold, we stopped just doing longevity testing and said that it was done. And this is an indicator how often these may have to be maintained in the field from a practical performance standpoint. So with that, we were able to successfully develop a testing methodology that helped us evaluate it from an individual performance, and then over time using longevity testing. We used 2 different soil types, 3 flow rates, and then we really only considered the direct discharge results once we saw that water was bypassing some of the practices. So out of the 8 proprietary practices, really only 2 of them satisfied that 80% requirement. But we noticed that the flow rate and the discharge method, played a primary role in how much sediment was retained, and it was reduced when you went to higher flow rates. And then those catch basin inserts that experienced longer periods of overflow experienced reductions in total sediment retention. So these were some of the interesting results that we just obtained through the lab testing. And I will end it there and open it up for questions.
Was your homemade version continuing to be tested, or?
We tested it just for fun, and it was in the 60% range.
Or was it in that middle group?
But it wasn't part of that data set you saw.
Oh, okay.
But we just did that so we could evaluate it using none of the manufactured products, just the testing apparatus.
How do you think the introduction of trash and larger sort of total solids in this whole discussion would affect performance?
It could affect performance. I bet you if you start getting trash and debris and grass clippings and you name it, it's just gonna reduce the flow capability or flow through capabilities of those different practices, which is going to end up causing maintenance issues down the road. It could cause flooding onto the roadway, and it could affect their performance over time. I'll put it out there that they probably all could be improved. There could be a point in time where they could achieve 80% or more, but I think it's really going to come down to the practicality of being able to maintain them over time. We'll take one more question.
Were the size of the dams essentially equivalent, or were some much bigger than others?
I'd say they were relatively equivalent. Some came in different shapes. I'd say they were relatively the same size because they fit in the same catch basin, but they just had different shapes. They had different features. Some were a lot sturdier than others. Some were just bags that hang from a wire mesh, and they were made of different materials. So there was all shapes and sizes, but they all fit into the same catch basin. So to keep us on time, I'm going to pass it off to Wes to introduce the next speaker, who's going to thank you.